So I still want to do gauge theory and gravity. So I'm going to try to give you an overview of quantum reference frames in gauge theories now, and then gravity afterwards in the next lecture. So so since we don't have a lot of time, this will be necessarily a bit more qualitative and of course. And so, but let me, actually maybe if you want to have some references, so classical, so these would be dynamic reference frames, continuum. If you want to know more about this, there's kind of the references, but you can, if you care about this, then so this is for the first part where we'll talk about classical dynamical reference frames. And then to reintroduce them carefully, I would need a covariant phase space, which I'm not sure everybody's familiar with, and so it would take me some time to use those tools. So I will do that really more qualitatively. But then when we go to the quantum theory, the tools I've already introduced are enough to understand what happens in that stage. So, but first of all, we're going a little bit back to, so we started out by special relativity versus quantum reference frames. So let's now do special relativity versus gauge theories. So here, we have gauge transformations, so Frank transformations. So here they were just, some lambda mu SO1. And now we're going to be given some gauge theory. So we'll have some kind of structure group. So for instance, U1 for Maxwell theory or quantum electrodynamics. And then really the gauge transformations are, so that's called G. And the gauge transformations are G-valued space-time functions. So the structure group is, of course, so this is a finite dimensional group. And when you take suitable G-valued spacetime functions, it means you have a structure group at each point in spacetime. So very clearly, that's an infinite dimensional object. So now, in general, you have to specify also what kind of G-valued spacetime functions you mean. So when we are in Minkowski space, for instance, there would be G-valued functions with the additional condition that they fall off sufficiently quickly towards the asymptotics. So, zero support on the asymptotic boundary, so it's about small gauge transformations. And so that tells us, so far, we also wanted to use the internal reference frames. Maybe I should really say also internal. This is classical. So we wanted to use the. Here the reason I'm emphasizing this is again is that we had the internal frame orientations. So they take value in the group. If you remember this. So we use the frame to deparameterize the group that we're interested in. So that tells you already that if I have an infinite dimensional object, I want to deparameterize it, then the reference frames that we now have to deal with can no longer be finite dimensional, so they have to be fields themselves. Let me call this here G. So the set of G-valued spacetime functions. Let's call this. Like this. I want to deparameterize G. So whatever the frame field is. So frame plus the field. Then using gauge theories, it's a little bit simpler because gauge transformations act locally. So let's think of the fiber bundle over your space-time manifold, and then the structure group just acts locally. So I can really start by locally defining these reference frames in gauge theories. And so really what we want to have is something that takes value in the group. So so in these papers, I think we called the frame, let's call it U. Okay, so and U, I'm going to put a phi here in a boxed bracket, where this here is not a scalar field, it's just the label for a field configuration. Okay? So phi is just an abstract label for configuration of your field space. And now, so it's supposed to be a field, so I'm going to do round brackets for x, and then, okay, x is now in your manifold. So we want to have something like this. And now, so we want to use this reference frame to deparameterize these gauge transformations. There will be many different ways in which we can do this. But for gravity, I will just give you basically what the ideal reference frames are. Just that these U phi x, that this takes value in the structure group itself. So we have literally, remember, we want to have configurations of the reference frame that are labeled by the group elements that we want to deparameterize. In this case here, of the tetras, they directly, the configuration itself is group element. So we're going to do the same thing here now. So I'm meaning for each x and phi, so this is really for all x and phi. Okay, so it takes value. And here this is the structure group now. So it means at each point in space-time it takes value in the structure. And so, and then gauge transformations, okay. I ordered these pens in a way where I thought they would work better, but they work for 1 minute and then I have to replace them. Okay, this one already looks bad. Gauge transformations. Here we simply had that E goes to lambda E. So the group acts on itself, and so we're going to do the same thing here. So what we want is that okay, I'm going to define it locally at the moment. Okay, so let me write it. So Gx, so G of x is in the same group. So for each fixed x, it is structure group valued. And I'm just going to write a right triangle for the group action on the reference frame. And what I want is that is the natural group action. Okay, so I'm going to take the convention and it's going to act just by multiplication. I mean, this group value, that's group value, so I can just multiply. I'm going to drop the phi label because it's a bit annoying to carry around. So phi implicit. It's important that this phi dependence makes clear, of course, that this is a dynamic parameter. So it depends on the dynamic property. And
sorry, here phi is a gauge invariant field, or it can transform.
Oh, phi.
Phi.
Well, phi is just an abstract label for a point in free configuration space. So it's not a field. Phi is not a field. So it's a point in x element m. So then you can write phi element f. That's field space, and phi is just a point in field space. If you think of the field configuration space as a manifold, phi is just one field configuration, but phi includes every field that's in the theory. So in the gauge theory, for instance, phi will include, of course, the connection, any matter, and so on that you also have.
Okay, not necessarily. Gauge invariant field. F means that.
Oh yeah, no, it's not necessarily. Yeah, so kinematical.
Okay.
So this is at this point the kinematical field configuration. Of course, if you want to, but as you be careful with this. That's why the covariant phase space is useful. At the end of the day, you want to go to the space of solutions. Which in standard gauge theory is equivalent to posing constraints, so that means you are actually on one shell. The many properties of the phase space, they actually depend on the one shell. So that's why for the moment it's not so important. So then this here, this transformation law is going to be our analog of this here. And now, maybe let me just give you immediately an example. H theories, so GTS. And an example, the simplest one probably is Wilson lines. So you could imagine having a point x here, and then I have some asymptotic boundary. Maybe I'm not in Minkowski space or something, doesn't really matter. But if I choose the gauge group, so the gauge group is this here, not the structure group, and it's some g value space-time functions that fall to 0 here. Then this point is a good anchor point for a Woodson line, and it means large gauge transformation can change it, but they are not considered gauge transformations. So then I can just define my u of x. Well, it's gamma here. So Woodson line. So we have just e to the minus gamma a, where a is the connection. For whatever the field is. So Mills theory or Maxwell's theory. Then as well known, clearly this guy for each x value in the all x will take value in the structure. And now you can also realize that that if I do the convention, or in any case, so if I look at now a gauge transformation that acts somewhere, so some small gauge transformation. So I think I have to orient it this way. So let's say I do a small gauge transformation. Okay, by the way, here I guess I should put a half order if it's not theory. That's if I do a small gauge transformation, so something that vanishes asymptotically, really all this will do is, so let's call that g of x. Then it will have indeed that g of x acting on this u here is exactly g of x. G of x will be satisfied in this case, right? I mean, and the gauge transformations, Wilson lines transform by G Wilson line G inverse, right? But if I take a small gauge transformation, then the G inverse on the other side is not there. So that gives you a nice realization of the ones you have here. And then, okay, we can look again at reorientations. It's also done. Reorientations. Remember, this was this other matrix AB that acts on the frame index. So it's a second representation of the Lorentz group. And then for quantum reference frames, remember we had gauge transformations that were also done. We had for QRFs, we had that gauge transformations have the property that they act by left multiplication in the convention that I've chosen, and we had that reorientations. So this is gauge here. We had that reorientations. These VRs, if you remember them, they would act from the other side. So the important thing is that there's two different representations of the group. And so what's the analog now of frame orientations here? There's many ways in which you can realize them, but one way is you do an asymptotic transformation, a large gauge transformation. So if I do a large gauge transformation with zero support on X, then I realize, so for example, large gauge, let's call them different, we can call them G tilde of X, so it's not, so it's not in that group there. So with let me say Gy with G tilde X being the identity, so it has trivial support here in the bulk. Then again, by the properties of the transformations of the Wilson line, I will have that G tilde of X. And I'm gonna, so here I use the this triangle symbol. I'm going to use some other symbol called like this for the action of this different representation of U of X, and this will just be U of X, G tilde X inverse. So it's okay. Is that going to be I guess most people know how Wilson lines transform. So if you have the Wilson line, so you have what's called a Z here, XZ, and in general, and there's some arbitrary gauge transformation, so small or large. This will transform as Q of X to G inverse at Z. So that's a standard transformation of the Wilson line. And so, I mean, this follows from this definition. Okay, I mean, I guess if you haven't seen this in gauge theories before, what I'm using here, I guess I should say that is that. So, to the higher energy physicists, that will be known, of course, that information maybe you know this. So the action of gauge transformations on the connection. This is G inverse minus D G inverse. So, for instance, with special cases, of course, in QED, you have U1 transformations, so they're cumulative. So you would have something like G is e to the I phi of x for some phase. So U1 in QED. Okay, then this part obviously cancels here, right? So there you would have dA is just this part is left invariant. And here, okay, you can convince yourself that this will be this. You just get the phase of the, sorry, no, the elementary, so it makes sense it would be 0. So, I mean, these are the standards U1 gauge transformations in maximal series. So this here is just a generalization to non-linear series. And anyway, when you use this transformation law of the connection, you can convince yourself that these Wilson lines under gauge transformations transform in this way, which I'm writing it up here. So then you can see that what we want to have for the property of gauge transformations and frame reorientations is actually realized by Wilson lines. And it's really exactly realized in the same sense in which we have realized it with quadratic space. There's two different representations, one acts to the left, the other one acts to the right.
Okay, so this large scale transformation X is at the boundary or in the bulk?
Yeah, no, so it should be at the it should be at the boundary, of course. Yeah, you're right. So well, no, I mean, okay. So here, okay, the 2 points that you pointed out a little bit precise what I did here. Here you should still keep in mind that there's something like this, right?
Yes.
So in the writing it just as a function of x is a little bit imprecise. I mean, because it acts on a field, right? So I would maybe just write it like this. Then, okay, sorry. Then when I'm now I'm really being a little bit imprecise because I'm actually you of course right that this here would be like this. But the thing is, when I have a fixed Wilson line, then I can't just associate this. Then you just call this here, let's call this h of x inverse, because there's a z. So there's a 1-to-1 correspondence between x and z. So that's why I can write it as a group element nx. So this requires, of course, that I have a fixed set of Wilson lines. But the other was a. So here, it's x. That's 1-to-1 for Wilson congruence, if you like.
Excuse me, if we do not have boundaries, what is the reorientation?
Yeah, so then it works a little bit differently. There's several things you can do. You can do a two-sided Wilson line, and then you do a double dressing. You can do this. You can also that would still be group valued. But for instance, you could also attach a Wilson line to some spinner somewhere else. So you have a half-dressed Wilson line, except when you dress it to a spinner, it's no longer exactly group valued. So it will not be an ideal reference frame, but it's still a valid reference frame. Yeah, so that's the that should give you an idea. So there's a general you can do a lot of different things. And also, you don't have to use Wilson lines, and you can also use other kind of dressing things. Just for simplicity. Yeah, so then maybe let's just go crash course further. And so relational addressable observables. So here, and something like Of course, here I could again also put some other group elements here, so I could also so this here you should think of this as SA in the identity when the frame is the identity configuration, but I could also, for instance, write something like SA of lambda something like lambda so this would be generalizing this, you have a frame orientation dependence, also in the relational growth of special activity. And now, we're going to look at relational observables, and suppose we have such a frame that's considered some, let's call it Fs again, and Fs is somehow functional. Sorry about square brackets, I mean it's a functional, right? So it's a functional field configuration space, really, I should think of it as a function. And now, okay, we call the reference frame U for some reason in these papers. Which I call an R, but anyway. And now, I can again do this at the orientation G. And then what we're going to do is, so we have some function Fs, some functional Fs, and then we're going to address this by a negate action by U inverse. So this is for group value frames. And so when I have, so U takes value in the group, in the gauge group, or in the structure group. This one here also takes value in the structure group. Whatever the gauge group is, it has an action on the functionals, so on the fixed space functions. So this will be defined, right? So I mean, for instance, this triangle action, if you're dealing with connections, I mean, it will be defined by this. So the gauge theory comes with a definition of that. And then we can check that this thing here is gauge invariant. So we can check this by looking at G prime O. This is so this would be a G prime, and then have this U inverse this. I'm just going to drop all these phi's here. The thing is, okay, it's a gauge transformation that acts on all the dynamical fields, so it will act both on U and it will also act on Fs. So this will be equal to G prime acting on U. I have this G inverse here. That was the inverse. Then I'm going to crash this onto G prime acting on Fs. I'm allowed to use because again the gauge transformations, they will act on each of the dynamical fields individually. And so now you can recall that this guy here, so this is nothing else than G prime U the inverse, and then G prime I'm just leaving it in a somewhat abstract form because the precise form of that equation depends on what the functional fs is. Right? And yeah, so basically, when you think about this here, I mean, this is here. Okay, well, I forgot to say, of course, that there's something like this G1, G2, Fs. So this is as so because there's an inverse here, this G prime will cancel that G prime. You have again that this is U G inverse minus 1. So I'm using this property. So I'm only looking at what G prime does. So the gauge transformation was G prime. It acts on this piece, it acts on that piece. And this piece here, well, it's just by here I'm using the covariance of the frame. So it's G prime U. And because there's an inverse here, so crash onto that G prime and cancels it. So that's the gauge invariant object. And now, so this gauge invariant. Then we also explain why you can think of this as, so this is the relation observable measuring S relative to U. I use an orientation G. So O of S, U of G, we just showed that it's gauge invariant. So to see that this is, so it's Fs, so this measures Fs conditional on U being in orientation G, so here I put it X, G of X. And the way to see this is gauge invariant. So it means the value of this, of course, doesn't change in which gauge I'm going to evaluate it. So I'm free to gauge fix it in any way I like. It doesn't change the value. And I can simply gauge fix it to be U equals to G. Right? So when I gauge fix it to U equals G, this part cancels. So this is how you see that this observable, it gauge invariantly reads the value of Fs on that point, or that intersection of the orbits where the gauge fixing surface, where the reference frame is an orientation G. Okay. So variant gauge, then fixed gauge by U equals G. Okay, so I'm allowed to gauge fix it this way. It's a complete reference frame actually, or assuming it's a complete reference frame. And that gauge you can also do, of course, in here to make sense of this, or not reference frames. So, and then the other thing that we can also see is when we again look at reorientations. So I suppose I wiped this off, but if you recall what I had there, so that's so that's G tilde. This over here, and this U inverse, so that's what we had. And now if you apply this here, and you do now the action of these reorientations on O Fs U D, I can of course act with this on this relation observable. And so what will this do is, it's now important that this is a reorientation that doesn't act on whatever the system degrees of freedom are. So in the picture that I had there, you know, when I sent in some gamma and maybe I'll call it Z and X, you could imagine, so this will become relevant for finite subregions. So we could have, for instance, that maybe this Fs only has supports inside the subregion, but not here. Okay. So that means, in particular, if I do a large gauge transformation here, it will transform the reference frame, but it will not do anything to anything inside the region. Okay. So this way, I can actually realize the reorientation. So reorientation, really, in the same sense in which we described it before, that it doesn't do anything to the system; it only changes the reference frame. Okay. So this is how, in this case, we should think about it. So it doesn't do anything to this, but it changes this guy here. But then, so it'll go into here. But that's the same. So actually, this will be inverse there. So yeah, I think this. Yeah. So then you can see here. It will actually translate. Again, the label of the relation observable, as we saw it also in reference frame. You see that's a realization of this normalization.
But does it change boundary condition of the configuration?
No, so that's the thing, whatever the large gauge transformations are, they have to be consistent with the global boundary condition.
Okay, but your concept should be consistent.
But the thing is, so that's of course one general thing, but it turns out, so I'm just using these large gauge transformations as the simplest way of thinking of these reorientations. It turns out there's many more ways we can do it. For instance, okay, it's also something we showed here. I use I-knots, but you could also, for instance, attach it to scribe plus minus. And then you can add actually soft or hard radiation without doing a large gauge transformation, and we'll have the same. But that's the simplest way of thinking about it. Okay, so is that clear? I'm just changing the U inside, and it's equivalent to translating that data there. So we realize this structure that we already saw a couple of times. Okay, so I think that's maybe all I wanted to say about the comparison with special relativity. So I'm now going to be a little bit more qualitative for what we can do with this classically in the context of finite regions and edge modes. That's obviously the motivation for us to look at this in gauge theories. I don't have anything additional. At least not sure what I want to do. So we could now think, so as you have seen, for instance, in one of the talks, you could think of a finite region in some global space-time, it could be part of Minkowski space. And the question is, how can we describe a finite region in gauge theories in a consistent way? And then indeed sometimes you hear the message that somehow finite boundaries break gauge invariance, but really strictly that's not true. And the point is just that we need to define what we mean by the subregion. So in gauge theory is not geometrically, but by the subregion theory in the sense of the field content, we need to define it in a gauge invariant manner. So we're going to define a subsystem gauge invariantly, so we need to define a relative to a reference frame. And so you can also think of this here as maybe a here. Okay, so there have been really the first systematic work on looking at subsystems in gauge theories, and discussion of edge-modes were a bit earlier, but the first kind of systematic discussion of finite region theories was done by Donnelly and Laurent Fidel, so advisor of Tarak, and Yuki has worked with him quite a bit, no? 2 years ago. And so what they showed is, so in contrast to what I'm describing here, they were really looking just at basically at a causal diameter of some spatial region sigma. They just looked at that in isolation without looking at the global theory. And then they looked at the phase space structures that you get from the covariant phase space that I've described to you. And basically, they argued that you needed to add some degrees of freedom on the corner. So the corner is really from the causal diameter view what looks like the corner here. So it's a spatial boundary with the entanglement surface. You needed to add some fields on that corner. They called it G, and okay, I'm just gonna call it U because we use And then they showed, so they argued that you need to extend your regional phase space by these additional degrees of freedom. Actually, in that paper, they never called them edge modes, but later on, everybody calls them edge modes. But anyway, and then they showed, okay, you can slightly extend your phase space structure, the symplectic structure with an additional corner piece. When you do this, then you get a gauge invariant phase space, and the base that's also conserved, and blah blah, those kinds of things. And then they also showed, okay, I have new degrees of freedom. I can actually address some of the degrees of freedom here on the corner with these new degrees of freedom, these edge modes, and I can actually construct new charge operators. And so this led to corner charges. And really, in gauge theories, it's mostly electric flux operators. And then they showed, okay, they satisfy a nice algebra that basically corresponds to the Lie algebra of the structure group, but at each point on the corner. So that's column Q of X really, and then you have for the A for the whatever the Lie algebra dimension is of the structure group, and then you have some QB, and then it satisfies some FABC or so of whatever your group is. And okay, and then suitably extended here with X, Y, and details don't really matter. But the point is that basically you get a symmetry algebra, and these are gauge invariant operators, so it's a physical symmetry. And these were often they're often called boundary symmetries or corner symmetries that are generated in this way. But they never really explain how you're supposed to think of these edge mode fields that just drop from the sky, and they're just postulated by hand. So they just added them by hand and added them to their original phase space. And then, okay, there was a lot of debate in the literature for several years with people looking at this, and a lot of controversy because some people, of course, didn't like that you have to add stuff. And for instance, Aloriello, Enrique Gomez, and some collaborators working at the same institute, so Perimeter Institute was kind of the hub of this in the world, and there's different views on the inside. And so they rather looked at, for instance, also regional phase space without extensions. And then, okay, they showed, oh, but you don't get any symmetry algebras in that case. There's no boundary symmetries except very special ones that are not interesting. And so, and then, there was conflict in some sense in the community at some level of how to think of these things. And really, okay, what we did is we zoomed out of this picture of looking at the region in isolation and asking, we should think of it as a sub-region on a global space-time and ask how the symmetry structures and all that stuff, how that relates to the global symmetry structure and the global gauge structure. That's why I'm drawing this here in the larger space-time. And so one thing that's, maybe I should mention these names, so a lot goes back to this paper, and it's, I would say, for this edge modes and gauge theory, probably it's kind of a seminal paper. It's 2016 or so. So it's about 9 years old, not too old. Okay, there's a lot of other stuff that comes afterwards. What I was saying, oh yeah, so basically our attempt was to make sense of this by embedding it in a global space-time. Okay. We looked at it also with time-like boundary to have a more dynamical rather than such a canonical picture. You don't necessarily need to have it. And okay, now remember what I forgot to say. So in Donnelly and Fidel, they also postulated the transformation properties of these edge modes. They distinguished exactly this gauge transformations from symmetries, and they postulated also this for gauge transformations. You have U going to GU, and for symmetries, U goes to U G inverse. Right? So that's what they postulated. So using, because they never really explained what an incarnation is of these U's, right? So they just postulated, and then they showed, oh, if I have a U that has these properties, then I can extend my phase space nicely, and I get a nice gauge invariant phase space structure. And I should also say that the charges that I mentioned that give rise to these boundary symmetries, they correspond to these symmetries. So that's basically the generators of these. Well, okay, in the gauge invariant form. So, but now you see that if I use Wilson lines, I get all that for free. Okay? And so, so this is the first paper that I cited in the beginning of this lecture. That's where we first discussed this. So we used the congruence of Wilson lines to set up an edge mode reference frame on the boundary. So really, it's a realization edge modes by Wilson lines. I mean, it's just one realization. It doesn't have to be, there can be others. Okay? So, but the thing is that then here, for x on this corner, you can define a u of x then in that way. Well, okay, I needed it, but in terms of a Wilson line, you attach to sort of boundary, and you get exactly all the properties that they had postulated. And in particular, for them, it was also important, really, that they also postulated that that U can be varied independently of other regional data. So that was also postulated, so you just add it as a new degree of freedom. And you see that you also get that for free when the Wilson lines have support on the positive complement of the subregion, that you can vary U independently, because it will depend on the connection to the complement. Okay. So in that sense, you get actually all of these, what they postulated is realized.
Sorry, so
yeah.
in the original framework, what was U there?
What was it?
What was the U? I mean, here you're saying it's.
Well, yes, I mean, so they didn't. I think they just called it G of X or something. But now I use G for the gauge transformation. So
it did, but it's not.
But it's the U. I mean, it's the U that I'm talking about. But it's just that they didn't give an explanation of what this U is.
Yeah.
It's just it drops from the sky, some abstract object that transforms this way. When you have it, then you see, oh, I get nice phase space structures, these corner symmetries, blah, blah, blah. But then you see with Wilson lines you get all that for free, so you don't even have to. So it is true that of course the U in this way have to my regional phase space, I'm adding it by hand. But when I view it in this way as being part of a global theory, it's not a U degree of freedom I have to add to the theory. It's always there. It's just a composite degree of freedom that I build in a non-local way out of the degrees of freedom in the complement, but has all the properties that they want. And so, yes, from the point of view of the global theory, there's nothing new there. So of course the convention which Wilson line congruence I will choose, and the point is I choose a different Wilson line congruence, it's a different point reference frame again. Okay? So the Wilson line congruence defines the point reference frame, so the edge mode reference frame. And yeah. So, and then the thing is, so I mean, in these papers, the first one really describe how to build a regional theory from the global one. So, okay, it's a bit technical, but I just give you the intuition. You take the global space of solutions of the theory, and then you do a kind of post-selection. So you build gauge invariant boundary conditions that you want to have realized on the boundary. You can do this by taking edge mode rest observables, where you want to have, for instance, that maybe the electric field is fixed to be whatever the normal electric field is supposed to be 0 or something on the boundary, or you fix a addressed version of the connection on the boundary to be something, some fixed profile. So of course clear that when I do this, not every global solution will be consistent with that, but a subset of solutions will be consistent with that. And basically this post-selection procedure isolates or picks out that subset of the global space of solutions that's consistent with the boundary conditions that I want to have. And then I look at that subspace of the global solution space, and then, okay, what I then do is, the only degrees of freedom that I keep track of is the truly regional degrees of freedom plus the choice of edge mode frame that I've chosen. That means these Wilson lines I will include in my regional phase space, and everything else in the complement I don't include. And then you can show, okay, I can write down regional phase space structures and have exactly all the properties that you want. So in this case, then you can also see by this realization that that the corner symmetries, they correspond to these postulated symmetries. What you see is that they correspond to the reorientations of the edge mode frame. Okay? And in particular, I can realize them as explained by large gauge transformations. And when you look at the corner symmetries in these cases, I mean, yeah, they're the same group as the asymptotic one, so it also makes sense that's a similar relation. And in some sense, you can think of the Wilson lines as basically pulling in the asymptotic symmetry group to finite distance. So it's a finite distance realization of this. Again, you can realize the corner symmetry group also without large gauge transformation. You can add hard radiation or soft radiation. You have more options actually. But the main point is, so the Wilson line realization shows that corner symmetries or edge frame reorientations. Okay. So now, so really summarizing that only qualitatively, but very clearly. So what we have done here is we take an edge mode frame that really comes from the complement. So when you address degrees of freedom on the boundary, so like using these relational observables here, and now you suppose that Fs only has support in this region here, and then you address it with this reference frame, that encodes, of course, some cross-boundary gauge invariant data. Okay? In particular, I can address, maybe I have 2 Wilson lines here, and I can address a half Wilson line here with it, and then I get basically a Wilson line that is asymptotically connected to the boundary. So that will be part of this of these relational observables. Okay. So that means when you make this choice of this external edge mode reference frame and you include it in your phase space, that's also a choice of which cross-boundary gauge invariant observables you include in your regional phase space. And that is really nothing else than you make a choice of what is AS, so this is the region. Really what you're building is you're building a relational observables describing S relative to the reference frame. And that includes some information, some cross-boundary information.
Excuse me, is there some canonical choice or preference?
No,
No.
there's not. And that's the whole thing. That's what comes also out of this picture is there's not a single choice of edge mode frame. It doesn't make sense to just think about them as one abstract object that falls from the sky. There's a whole continuum of choices you can make. And the point is, you choose a different Wilson line congruence, the algebra you construct is a different one. And subsets are relatively well tied. So different extrinsic Wilson line frames, they will all agree on the purely regional gauge invariant data. That should be intuitively clear because everything that's gauge invariant and has pure support in the region will be part of all of these guys. Right? But then each reference frame will add some cross-boundary data. And then it's also clear that when you look at the intersection of these algebras, they will agree exactly on the part of the system that's already gauge invariant, which is in this case the purely regional gauge invariant data that doesn't cross the boundary.
In that case, there's no corner symmetry or edge mode.
Exactly. So what I wanted to say is that these external Wilson line dressings is what in the second paper that I mentioned is what we call extrinsic edge mode frames, because they have supports in the complement and they give you all the symmetry structures that you want from this discussion there. But then you can in fact also do an intrinsic edge mode frame. Okay? So for instance, you could in principle also define, you can take a north pole here and then you shoot out Wilson lines somewhere else along the corner, and then you dress elsewhere some degrees of freedom, but it's a two-sided dressing. If you do this in a Abelian series, it does matter that I have an open point here, because the trace is trivial, I will still get some negation there in my case. And in fact, in a Abelian series, I can also you can also do, for instance, the Hodge decomposition of the connection on the corner. It's a closed compact manifold. The Hodge decomposition will give unique splitting. So maybe I'll write that here. Let me just say extrinsic edge mode frame is basically, for example, external Wilson lines, and you can have intrinsic edge modes. It's corner Wilson lines, or Hodge decomposition on the corner, or the Abelian series. So what that means is Hodge decomposition. So you have your connection on the corner, and there's a unique split into something that you can A tilde addressed and plus the phi tilde. And so there's a unique split between the exact part of A and the rest. And the point is that the rest is gauge invariant. So the exact part absorbs the entire gauge dependence of this object. So it's really, when you think about the Helmholtz decomposition in 3D, so this is a generalization of Helmholtz. So in Helmholtz decomposition, you also do something like in 2 dimensions, for instance. You compose it into a transversal piece plus a longitudinal piece, and the longitudinal piece is what's called chi, and that absorbs the entire gauge dependence, and this transversal part is gauge invariant. So you can do the same thing on the corner, and the more general way of doing this is also called Hodge decomposition. Then the point is this here, so this is gauge invariant, this is also gauge invariant. In particular, you have that phi tilde goes like phi tilde plus, I think before I call it, that's called alpha, if A goes to A plus E alpha. So it absorbs the full gauge dependence. And then, you can use this, so you can use phi tilde to build a U tilde, that's called e to the I phi tilde. So it's a local U1 valued object, so it's a group valued reference frame. Okay. So I can consider this this exact piece as the phase of the reference frame, and it's purely defined in terms of the internal structure, and so it will live only on the corner. So then, of course, I can also address everything with respect to this intrinsic edge mode frame. But then the thing is, for instance, this Hodge decomposition here, it's unique. So that means actually intrinsic frame has no reorientations. Okay. So that means in particular, you can't change phi tilde without changing A. So this thing that we wanted to have for reorientation is not possible. And that tells you already then, okay, I shouldn't expect any corner symmetries in that case. Indeed, you don't get any corner symmetries when you look at only the regional phase space that only contains the intrinsic edge mode. And that's exactly consistent with what Yellow and Gomez and so on described in their story. So they use a slightly different decomposition, but you could use the same that they use, you would get the same answer. So you see there's a qualitative difference in whether you use intrinsic or extrinsic edge modes, and kind of this previous controversy you can embed in a bigger picture, where both are correct. It's just they talk about different types of edge modes. Okay? So intrinsic edge frames have no reorientations. So then you understand from the point of view of the global theory, if you want to have a subregion theory, you want to make it consistent with this larger symmetry algebra, then you should go to the extrinsic description that they also in principle initially proposed. But it gives you a way of realizing that in the global theory.
For non-abelian theory, can we do a similar decomposition?
I mean, this is the Lorentz invariant theory, right? So the qualitative Lorentz invariant theory, of course, you choose a corner. I mean, a priori, it's the corner of the causal diamond.
Yeah, non-abelian.
Oh, non-abelian. Oh, sorry, I understood. So the Hodge decomposition, how exactly that works in non-abelian theories, we thought a while about it. We haven't really made it to work in a nice way, and that has to do with the fact that, well, you can do a Hodge decomposition in a non-abelian case also. It's just that here, the exact piece, I mean, I'm defining the standard exterior derivative, but the exterior derivative is not the covariant derivative that I have in the non-abelian theory. And, in order to have the properties that I want for the reference frame, I would want to have something that transforms the right way with respect to the covariant exterior derivative. So, if you're a little bit more imaginative than us, maybe you can work this out, but we didn't actually work this out so far. Which definitely doesn't mean that it cannot be done, but it's definitely a little bit more. You need to have the right perspective on it to apparently do it so far.
So maybe you already said this, but does the asymptotic structure of the bigger space-time matter at all? I mean, you can choose like different type of asymptotics.
Yeah. So it will matter for sure. So we get the so okay, if I want to have an intrinsic phase space, then it doesn't matter.
Right.
because it knows nothing about anything about large gauge transformations or so. It's completely, it's charged in a trivial way under large gauge transformations. But for the exterior, for the extrinsic type, it will of course matter because if I have Wilson lines that go to a global boundary, well, they're particularly nice, and as I mentioned, they kind of pull in the asymptotic symmetry structure completely. If you want to make that consistent with it, so for a causal diamond, it's not difficult because you don't really need boundary conditions. But if you want to make it consistent with the dynamics, it's also possible, but you have to actually define a new class of boundary conditions, which we totally missed in our first paper, but in the second one, we try to figure out what it is. Because they're not traditional ones. But anyway, they're kind of like Neumann and Dirichlet, but only for radiative data. You can think of them like this, basically. But it's clear that if I don't have a global boundary, then I can't quite do the same thing. And so then I would have to do, for instance, I could attach my extrinsic edge mode frame, say, to some spinner in the complement or so. But then I'm coupling to matter. And okay, it will still have some kind of reorientations, but these reorientations in general are not going to be the same group that I had before. Okay? Because you have to be careful with the matter properties, whether or not the reorientations that we'll have are consistent with a full set of SUN symmetries at each point on the corner. So yeah, so basically the simplest case, this would be is best described when you have an asymptotic. But in Minkowski space, you can do this. Okay, so then we have 20 minutes for our last gauge sequence. Was there any other questions? I mean, 20 minutes I cannot do a lot, so basically, so I mean what I've told you is all in the continuum, the classical continuum so far. To treat that at a rigorous level with quantum reference frames is a little bit difficult because these U's are fields, so okay, it's a bit more involved. But the thing is, if I do this on a lattice, everything that I told you so far in this course, especially the last 2 days, applies to that context, and you can realize that basically everything what I've told you here on the lattice. So I mean, the gauge here is just a mechanical system. If I have a finite lattice. And so we can imagine having some lattice, and for drawing purposes, I'm going to make it very regular. That you could, have something that's complicated, also in any dimension. The dimension doesn't really matter. But what we're going to be interested in is really, at the end of the day, we want to compute entanglement entropies now. So this whole business of subsystem relativity and relational entanglement entropies, I will also find this case now. So, is this legible that this is right in the back, or? Okay. So let's say this here is sigma, okay? So then this red thing there is now our corner. And then we can maybe call, I think green was bad, no? That didn't really work. Okay, yeah, blue is expired.
Oh, really?
Okay, so I think I only have 2 colors left. So so then, let's call this global thing, let's call that B for the global boundary. And on the lattice in general, if I'm also a non-abelian series, I have to introduce on the lattice, on the edges, I have to introduce an orientation. So we can think of something like this if you want, and so on. Okay. So the reason I need this orientation is, was that from down there? It works. But I think only for 3 seconds because those were and now, what is the kinematic Hilbert space now? it's for each edge, well, E is the set of edges in the lattice. I have a Hilbert space HE, and in fact HE is really nothing else than an L2 over G, where this is the structure group. So, works really well when you do that. Yeah.
In a box.
Oh, it was in the box. Okay, I missed that. That was blue. Anyway, so so this is our kinematic Hilbert space, and I think really the key thing that I need to tell you is that to really, so we have now structure group G, and I think I need to tell you a little bit more about the edge space. So for each edge, so, I mean, this is the regular representation that we've already seen before for ideal quantum reference frames. And so we have a group basis for each edge. So we have a covariant group basis. So we have G, E, and then we write like this as. And, for simplicity, let's think about it being compact. Write it as like G prime inverse G prime. Okay, so far, for frame orientation states, I always wrote a phi. That's kind of when they're Jano-Fourier states, but now when we use the regular representation, I'm just going to drop the phi for rotational simplicity. But they're really the same kind of states that we already looked at before. And now one thing is that this regular representation comes with two actions. So L2 over G is the regular representation. Comes with two G actions, exactly the ones that we want. So, in particular, so this here I call UE, so it means I have UE, well, this is one. And I also have a second one, which is again, let's just call it V, and G prime, G, E equals G prime inverse. So it comes for free. This representation has it built into it. Okay. And so, yeah. Now, what are the degrees of freedom that live on this Hilbert space? I have these link variables for each edge. So you sometimes write them as G hats. They're Wilson lines. Okay? So the link variables, you should think of them as basically you have a node here, and you have a node here, and this is E, and G hat E is the Wilson line. And the Wilson line from the initial to the final vertex. And in particular, this G hat E takes value in some representation of the group, which you can pick, could be the fundamental representation or whatever. Okay. So, so it's not to be confused with this representation. This is the quantum representation on the Hilbert space of that group. This representation in which this takes value is a separate representation. That's basically, for instance, the same representation that you would choose classically when you represent your Wilson line. So you have these link variables that you define on this Hilbert space, and you have two kinds of electric fields. And these electric fields are the generators of U and V. So I have two representations of G. So we also have two representations of the Lie algebras. And well, for instance, the ones associated with this one here we call the left electric fields, and the ones associated with that the right electric fields. They're related, they're not independent. I mean, they cannot be independent just by degree of freedom counting, but you can also write down the relation between them. But anyway, so yeah, we just write them as LE as operators, and they obey the Lie algebra of the generators of the D group. So it's just to give you a bit of an intuition of what the field content is. So the details, okay, of course, for precise formulation, they will matter. Understanding it thoroughly, but kind of picture I'm going to draw is. I don't have time to describe this. By the way, maybe I should give you the reference where you can read about this. This is a very recent paper. It's this is 2506. That's where you can read more about it. And so, so we have a kinematic Hilbert space that's just given by these edge Hilbert spaces. Then in order to connect it with a reference frame picture, what we want is Hkin as HR tensor HS, right? And so the question is now, how can we do this? Okay, I forgot to say that the gauge transformations on the lattice, they act node-wise, okay? It's at each node you have a Gauss law, basically. So it's, I think I should say that. For instance, we can have here some V, and then let's call it UV. Maybe put a vector there because I'm talking about gauge transformation of the whole lattice, so there will be G-valued lattice functions. Okay. And this here is, we can take a convention that we take UE G where breaks E in so what do you mean by this is? So the same transformations that I wrote down here on each of the Hilbert spaces for each edge, the representation of G. The gauge transformation will pick the convention such that at the node V, the gauge transformations, so there is a, because of this left-right business, we have to be careful with the orientation. That's why I introduced this, because then we have to be careful with the V or U. And for the incoming ones, so for instance for this edge, and for this edge, we would pick this left representation. For the outgoing ones, we pick the right one. It's a convention, you can do it the other way around. Okay, the reason I put a G hat, G vector here is because I have to run, of course, over gauge transformations over the whole lattice. So, and now what we want to do is we want to kind of refactorize the kinematic Hilbert space such that we can, using Wilson lines, to write it in this form here. Okay? And essentially what we want to do is now, R will be a spanning tree or forest really of Wilson lines. For the full lattice, so it means so when I say spanning tree or spanning forest, in the graph theory sense, so I can have asymptotic boundary anchored Wilson lines, because here again we will assume that large gauge transformations are physical. And then what I want is basically a congruence of Wilson lines that hits every bulk point once and only once, and that there is and if it is a tree or spanning forest, it means there's no loops contained in that set of Wilson lines, so there's no bulk gauge invariant degrees of freedom in that. Okay. So then we're going to visit every point in the bulk with one Wilson line. And one Wilson line is enough to fix the gauge at each node. So if we can do this, then we can gauge fix the full gauge transformation everywhere in the bulk. Small gauge transformation. So that's the idea of what we want to do. And now, suppose I have now my coordinate here, and here's B, and now I'm thinking something like this here as a Wilson line. So okay, one has to be careful with orientation here. It goes up. That's actually against the. Maybe let me not do this because then I have to tell you more. So let's assume I'm actually following the orientations of the edges. That is a little bit simpler, but the other case you can also do. So suppose this is a Wilson line. So we're going to be using that Wilson line, for instance, to realize a lattice edge mode, extrinsic edge mode here. Okay. So now what I want to do is, so here, to this guy here, I have a Hilbert space, which is E. So let's call this whole thing W. So E in W, all the edges here, the Hilbert space associated with this Wilson line is the Hilbert space here, 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 here. Right? And so what we want to do is now, we want to refactorize it. In particular, so you can think about it. So if you can think about this here, something like G1, all this G1, G2, G3, G4. So in the sense of the group orientation basis, so we will have something like G1, G2, G3, G4. So we have edge variables here, and what we're going to do now is we're going to refactorize that into Wilson line variables. That means Wilson line from here to here, Wilson line from here to there, Wilson line from here to there, Wilson line from here to there. It's exactly the same amount of information. So we're going to go now to G1. That is it. So go to cumulative node variables. So Q1 remains the same. Then I want to go to the second vertex here. And that one will be G2, G1. The next one is G3, G2, G1. The last one is G4, G3, G2, G1. So I'm just refactorizing my Hilbert space. You can convince yourself that this is unitary, and each one of them is still defined as still a regular representation in each of these factors. Okay? So this gives you then a refactorization of this HE and E and W, and it goes to another set of L2 over G, and maybe I'll call this there's a name now. So the point is we go from edge Hilbert spaces to Hilbert spaces you would associate with the nodes. Okay, so E and W, and then you have an HB, and each one of them is still a copy of that. Or really, you can maybe let's call it RV because it's the reference frame at the node V. And the point is it's L2 over G, it's a regular representation. So it means it's actually an ideal point reference frame. So the QRF at node it's an ideal one and has perfectly distinguishable orientation states. So that should give you a sense. So I'm running out of time for this, but I hope it's more or less intuitively clear what you're doing. So you're really taking these, well, I guess here this tensor product of over all the edges in the Hilbert space. And you're going to refactorize your kinematic Hilbert space in a unitary way, such that you have a part that only corresponds to the Wilson line tree, really, in the bulk. That's the reference frame, and then the complement, that's the system. And so, in particular, we can now look at the subregion here, and we can, we can choose now some extrinsic edge mode frame, just like we did it in the continuum. So you can do the same thing here. So what you would then do is, you can again define the subregion theory. And now the nice thing is that because these are ideal, so I can do the same construction for any of these extrinsic edge mode Wilson lines. Because it's ideal point reference frame, it actually defines you a beautiful tensor product structure on the gauge-around Hilbert space. So it actually gives you a factorization between what the reference frame calls the region and the outside. And so this is overcomes these non-listable issues that you have in all these previous constructions. So let me maybe just qualitatively say what happens. To explain that in detail would really take a bit of time, but so then realize lattice version extrinsic edge mode frame. The point is it's ideal. So that's really important. So it means that defines a tensor product structure on H, HPN. So the usual issues that people then argue, the gauge invariant Hilbert space doesn't factorize across what the region is and what the outside is. And it's true when you take a kinematic point of view on this. When you define what you mean by in and outside in a kinematic way, then that's correct, and it doesn't. But the point is, if I define in a relational way, so the gauge invariant way, what I mean by the in and outside, then it actually factorizes. So again, I can use the extrinsic edge mode frame. I really just do this page width reduction. And this goes from the perspective usual Hilbert space, so the physical Hilbert space, into a tensor product. And it will be the complement of the region without the extrinsic frame. I don't think I gave it a name. Called phi extrinsic or something. So this here is the extrinsic edge mode frame. I have to extract it, of course, from the exterior part of the lattice because I'm not describing the frame relative to itself. And then there will be a tensor factor for what that frame sees as the region. And this will, of course, encode anything also included on the boundary. So then you can compute relational entanglement entropies in the usual sense. So you just use standard von Neumann entanglement entropies on the, of course, on the physical Hilbert space or the reduced picture. You have a tensor product, so you can trace out this part in the usual sense, and you have a density operator here, and you just get a standard von Neumann entropy without any non-listable contributions. So in particular, this A sigma, this here, is isomorphic to the regional degrees of freedom relative to this phi extrinsic. So that's the gauge invariant description, that's the reduced description. There's a factor algebra. So it doesn't have a non-trivial center. Okay? So in usual constructions in lattice gauge theory, people work with these electric center constructions and magnetic center constructions. And here you see you don't have to have that. Of course, you're making a step away from this by going to a picture where you're defining what you mean by the subsystem associated with the region in a relational way. And so, and so we get no non-discriminable entropy contributions. Now, so of course on the lattice you can also define an intrinsic edge-mode reference frame. For a Höhn series, the same thing will work. For a Höhn series, there will again be factorization. For non-Höhn series, that's no longer the case. And that has to do with the fact that the intrinsic reference frame is an incomplete reference frame. I haven't really explained to you what that means, but it's not capable of deparametrizing gauge symmetries on the boundary completely. It has basically 1 degree of freedom too little, and that leads to an additional average in the picture, and that leads to basically a subspace of the tensor product in general. Okay? But now to connect with the usual stories, if some of you are familiar with it, how do you recover these electric and magnetic center constructions that people have usually constructed? And it turns out that, for instance, the usual electric center algebra, it's called A sigma E, so you can define that at the gauge invariant level. What is that? It's basically all the regional gauge invariant data plus normal flux, electric flux. Okay? So, when I say normal electric flux, you have to take the Casimir, so you have to square it, so it's gauge invariant. Okay? And that is of course contained in this algebra here, right? It's contained inside it. It is purely regionally defined, so it is part of it. But this algebra has more information because when I address this here, in particular, I can, I have this cross-boundary data of such a Wilson line, for instance, is in this extrinsic algebra, which is not part in this electric center algebra. And so now what you can show is that the electric center algebra is actually exactly the intersection of all possible extrinsic algebras. So that sigma E is really the intersection of relational derivals describing sigma relative to a given extrinsic reference frame. You take that algebra and you do it for all possible choices of extrinsic reference frames. You intersect them all. Then you get back the electric center. And you can also, another alternative way to see it, how you can get it is by looking at an electric twirl of any of the any one of these extrinsic algebras. So this is one way in which you can get it. You intersect all the extrinsic algebras. For this, the lattice has to be big enough that I have enough choice of extrinsic algebra, enough extrinsic reference frames, or the region has to be small enough compared to the full lattice. But I can also take any extrinsic algebra describing the region relative to any one of the extrinsic reference frames, on that algebra, you have this Korner symmetry group, the lattice incarnation of it. It's an electric Korner symmetry group. And I can G-twirl over that electric Korner symmetry group. I do an incoherent twirl of this physical symmetry group. And when I apply that to these extrinsic algebras, it removes exactly all the cross-boundary relational data. And so these the super selection sectors you get to these electric center constructions, they come from this incoherent G-twirl. The way you can think about this is that okay, I guess I didn't really explain this, but so the electric Korner symmetry group, well, it's a physical symmetry group, it's not a gauge symmetry group, but you can associate a physical reference frame with it, quantum reference frame, so it's not a gauge quantum reference frame as we discussed it so far. And it turns out the gauge invariant quantum reference frame you can associate with that electric Korner symmetry group as a Goldstone mode. You can think of this here as basically averaging over the configurations of the Goldstone mode. And now you can, in fact, do the same kind of construction with the intrinsic stuff. And if you take the intersection of all the intrinsically defined relational algebras, you get actually exactly the magnetic center. So it's really kind of beautiful what happens there. And you can also get the magnetic center construction by doing an incoherent twirl over a magnetic dual Korner symmetry group of the intrinsic algebras. By dual, I mean it's a Prof dual. So it actually only works in abelian cases. This last part, but the intersection works in general. So if you want to think a little bit about this, so this here is the part that has this non-distillable entanglement. You can actually use these. So in the end, really, what this leads to is a nice algebra inclusion structure and hierarchy. So you have I just call it the extrinsic algebras. That's what I have there. Then you have the electric center. Then you have an intrinsic relational algebra. Then you have the magnetic center. And you can use this algebra hierarchy to also write down hierarchies for relative entropies, and in fact, for this here also you get an inequality for von Neumann entropy. So in particular, the magnetic center entanglement entropy is upper bounding the intrinsic one, and that's okay. So basically what you see is you can think of this, you can think of these center algebras really as what all the extrinsic reference frames agree on and what all the intrinsic reference frames agree on. So it's a little bit, it's a bit like in special relativity. If you have different Lorentz observers, these center constructions, these algebras correspond to basically Lorentz scalars. What this quantum reference frame story adds to the game is basically all the frame covariance stuff you get on top of it. So it's like really, descriptions that are not Lorentz scalars, but physical observables that are, that actually change when you change, Lorentz frame. So you can really view this as, you're really adding to the game all the interesting frame covariant physics that was kind of completely missed in these previous non-relational constructions. I think I'll stop here then.
Any questions?
So your entanglement entropy does not contain the center contribution.
No, I mean it's just the factors.
So it's just you fix all boundary configuration, so only dimensional entanglement.
I mean the point is I'm computing. So this is a different algebra than this one, and I'm computing the entropy for this algebra. And this algebra is a factor, so it has no non-distillable part. This one has it. And you can reconstruct it from this framework here by looking at all the intersections or by basically averaging over the electric Korner symmetry group. Yeah. So this here of course has these super selection sectors, and it reproduces the previous constructions. Okay. One thing is that the G-twirl actually agrees with the previous construction on the extended Hilbert space. So there were previous discussions of the electric center algebra and then computations, they misdetermine the entropy compared to the extended Hilbert space construction. And surprisingly, even though we get the same algebra here, our computation of the entropy, you can see it actually reproduces the part that the extended Hilbert space has. So, seems like the previous extended instructions, they were actually missing the contribution.
Yeah, I didn't get why you rewrite the modes like using cumulative mode. Yeah.
Because I want to rewrite the kinematic Hilbert space into reference frame and system, and the original one doesn't have that form.
Reference. So like in this basis, what is the reference system and what is the system?
It wasn't like the reference frames. So it's the same as in the continuum that I described. So initially so I have initially H kin is just E in the total lattice of these Hilbert spaces. So a priori there's no split into reference frame and system. So what I want to do is I want to rewrite this as HR enter HS, but then I have to make a choice of what is R. So in here it has to, if you want to do this for the full lattice, R should be any spanning tree of Wilson lines. Because the Wilson lines, they have these reference frame properties, as I showed in the continuum, but it should also be clear that they have that here. And so, this here, these are edge variable based decompositions. And what I'm doing, which I wiped out, is I'm going from these edge variable decompositions of Hilbert space along the Wilson lines that define the frames. I'm going to refactorize that into Hilbert spaces that now that are not this times this times this times this, but that are this Wilson line times this Wilson line times this Wilson line times this Wilson line. You see? So that means every factor is now a reference frame for one of the nodes. So that's why I'm calling it this way. So I'm taking edgewise variables and I'm writing them in terms of and I'm going to factorization in terms of the nodes along that collection of edges. And at each node, the Hilbert space corresponds to the Wilson line connecting that node with the boundary.
But like you wrote a factorization between HR and HS. So here, what is the HR and the HS? I mean, like how is the HR and the HS individually spanned?
Well, so I mean, I did spell it out for gravity, but it would be you take the Wilson lines along the spanning tree. For each of the Wilson lines, you do this refactorization, and then the whole collection of that is your HR, and whatever is not inside the spanning tree is your HS.
I see. But isn't that refactorization changes the kind of space, for instance, I was wondering about the entanglement entropy. Yeah. So like if you consider entanglement entropy, you have to specify the spatial subregion and basically consider its entanglement between spatial subregion and its complement. Yeah. But like this, under this refactorization, I just worried whether this is a kind of non-local basis.
It is a non-local refactorization for sure of the total of the kinematic Hilbert space. Yes, definitely. But the thing is still, when I define the subregion, that's unaffected.
Okay.
I'll be taking the Wilson lines up to there. But it's true that in order to when I do the relational definition of what I mean by the subregion, from the point of view of the original kinematic Hilbert space, it is a non-local definition, because it's now the definition of the subregion relative to this extrinsic asymptotically anchored Wilson line. So you're right. So it's basically the trade-off is.
So the definition of entanglement entropy depends on which subsystem. I mean, like you can't compare the entanglement entropy of some subsystem to other subsystems.
No, that's exactly the thing. This algebra hierarchy allows you to compare that. So that's the beautiful thing of this. Right? So what is true is that if I pick two different extrinsic reference frames, subsystem relativity will apply. So I mean, so that's why I have to have this intersection is basically subsystem relativity. Right? So I have two extrinsic reference frames. They agree. If they don't overlap, then the only thing they will agree on is the regional data that's already gauge invariant without addressing to any exterior reference frame. That's why this needs to be big enough for this to be true. So what I need is that there's at least 2 extrinsic reference frames that don't overlap in their edges. And as soon as that can be realized, then you find that the intersection of the whole thing is the purely regional gauge invariant data. That's gauge invariant without extrinsic dressing, and that's exactly the electric center. So then, yeah, it gives you a much bigger perspective on it. So a really relational perspective, where yes, if you define it relative to the reference frame, it's a relational entanglement entropy. Because of subsystem relativity, I pick a different extrinsic reference frame, the entanglement entropy will be different. And then I can of course look at what would every extrinsic reference frame agree on. That's the electric center algebra, and then I recover, the whole thing. But then the nice thing is that you can write down an entropy hierarchy using this stuff. So and that has to do with the fact that this map is a G-twirl, and the G-twirl is a CPTP map. And then, okay, you can use relative entropy arguments to prove that even the phenomenon entropy satisfies an exact inequality between this. So relative entropies, it's much easier to show that there's, by monotonicity of relative entropy, that there's a hierarchy of relative entropies, but the nice thing is that you even have the phenomenon entropies inequalities. It's between these 2 and these 2, but there's no phenomenon entropy inequality between these.
Okay, any more questions?
I have questions. So when the Hilbert space is factorized successfully, and then you take the trees, is the tree still divergent or finite?
This is what, sorry?
When the Hilbert space factorized successfully, and then you compare the entanglement.
But it's a standard Hilbert space trace in this case.
Divergent, still divergent.
Well, no. I mean, it depends on your state, of course. I mean, if you pick G to be a compact group, and then you have L2 over G, it's an infinite-dimensional Hilbert space.
Yes.
But of course, there will be states when it's not divergent.
Just the vacuum state.
I mean, on the trace, I could of course take something like completely mixed state, the identity, and then I take a partial trace. Well, okay, then I get divergence. But if I take some like pure state or so, generically, this would not be divergent. I mean, take any finite rank state, really, the trace will be okay. It's just a standard Hilbert space trace.
More questions? I guess not, then let's thank Philipp.